The problem with today's AI isn't simply that models are getting bigger, it's that they keep computing, even when there is very little useful information to process. Every time a transformer processes a token, enormous matrices are multiplied. Inside those matrices are billions of numerical operations, many of which involve values that contribute very little to the final answer. At hyperscale, this becomes a physical problem. Modern AI data centers are moving toward megawatt-scale power consumption, and much of that electrical energy ultimately becomes heat. Cooling systems must continuously remove that heat from GPUs and other accelerators. As compute density increases, cooling becomes increasingly difficult, not because the mathematics is abstract, but because physics eventually imposes a limit. And this creates a fascinating comparison. The human brain operates on roughly 20 watts of power while performing extraordinarily complex perception, reasoning, memory, and motor functions. A large AI system can require orders of magnitude more power to perform narrower computational tasks. So why is biology so much more efficient? One answer lies in something transformers largely ignore: silence. The brain doesn't continuously compute every possible connection. Neurons communicate sparsely. Most neurons are inactive at any given moment. Most connections are not firing. Computation happens selectively when information actually matters. Traditional neural networks, however, tend to perform dense mathematical operations. Imagine a matrix containing 1, 0, 0, 0, 0, 0, 0, 0. The zeros contain no useful information. Yet conventional hardware generally processes them as part of the matrix multiplication anyway. A multiplication by zero still participates in the computational machinery. Data must be fetched, moved, scheduled, multiplied, or accumulated, and the hardware must consume energy to discover that the contribution is zero. This is one of the deeper inefficiencies of conventional silicon. It treats absence of information as something that still has to be processed. Biology does something radically different. If there is nothing to communicate, it stays silent. That leads us to a fundamental question. What if the next generation of AI doesn't become more powerful by computing more, but by learning what not to compute? Instead of an always-on transformer, imagine a system where computation itself becomes sparse. Only the relevant neurons activate. Only the important connections communicate. Only the necessary portions of the model consume energy. And suddenly, the goal of AI research changes. We are no longer asking, how can we perform more computation? We start asking, how can we perform less computation and still get the right answer? That is where the biological secret of sparse communication becomes one of the most important ideas for the future of efficient AI. The key event inside a biological neuron is the action potential, the electrical spike. Instead of continuously transmitting a floating point value like a conventional neural network, a spiking neuron can communicate through a discrete event: spike, no spike, spike, silence, spike. The important information isn't necessarily the magnitude of a continuous number. It can be when the spike occurs. This is the foundation of spiking neural networks, or SNNs. In a conventional neural network, activation might look like 0.137, 0.492, 0.731, 0.284. The system continuously manipulates numerical values. In an SNN, the representation can instead look like 0, 1, 0, 0, 1, 0, 1. The 1 represents a spike occurring at a particular moment. And this introduces something conventional neural networks largely treat as secondary. Time becomes information. Imagine two neurons that produce exactly the same number of spikes. One fires at 3 different moments. Another fires the same number of spikes, but at different moments. The spike count is identical, but their timing is different. That timing can encode information. This is called temporal coding. A single spike doesn't have to carry only a simple yes or no message. Its position in time can encode information about an input, a feature, or a decision. And now we reach the mathematical reason SNNs are so interesting for efficient AI. Traditional neural networks repeatedly perform operations such as y equals w times x. A weight is multiplied by an activation. Then thousands, millions, or billions of these multiplications are accumulated. SNNs can shift much of this computation towards something simpler: accumulation. A neuron receives incoming spikes and accumulates their weighted contributions inside a membrane potential. Conceptually, V at t plus 1 equals V at t plus the sum of Wi times ISI at t. The membrane potential integrates incoming events over time. When it crosses a threshold, V at t becomes greater than or equal to theta, the neuron emits a spike. Then the process can reset or continue according to the neuron model. The important idea is not that multiplication magically disappears. The important idea is that multiplication doesn't have to happen continuously at every time step for every activation. If no spike arrives, there may be nothing to accumulate. Silence becomes computationally meaningful. This creates a radically different computational pattern. Dense neural network. Multiply, 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 accumulate. Spiking network. Silence, spike, accumulate. Silence, silence, spike. The second system can dramatically reduce the number of active operations when neural activity is sparse. And that brings us back to biology. The brain isn't sending a continuous floating point number through every synapse at every instant. It communicates through events, spikes, timing, silence, selective activation. That is why SNN research is so compelling. It isn't simply trying to make neural networks smaller. It is trying to change the fundamental unit of computation from continuous numerical processing to event-driven communication. But there is a major challenge. Modern transformers are exceptionally good at processing language because they operate on rich, continuous representations. SNNs, historically, have struggled to match that flexibility and accuracy. So researchers aren't necessarily choosing between transformer or SNN. Instead, a new direction is emerging: hybrid architectures. Part of the model performs dense high-level representation learning. Another part exploits sparse event-driven computation. And by mid-2026, this hybridization is becoming one of the most interesting directions in efficient AI research. The question is no longer simply, can we build a spiking neural network? The more important question is, where should conventional computation end, and where should spikes take over? The real breakthrough may not be replacing transformers with spiking neural networks. It may be combining them. A traditional transformer and a spike-driven transformer can look similar at a high level, but the way they represent and process information is fundamentally different. In a conventional transformer, attention begins with continuous vectors. For every token, the model generates Q, query, K, key, and V, value. It then computes attention using QK transpose divided by the square root of D sub K, followed by a softmax and multiplication with V. This is extraordinarily powerful, but it is also computationally expensive. Now imagine replacing the first stage with a spiking system. Instead of passing every feature forward continuously, an SNN layer receives incoming signals and asks a simpler question: is this information important enough to generate a spike? If the accumulated membrane potential doesn't cross the threshold, there is no spike. Nothing needs to be communicated downstream. But if the signal crosses the threshold, a spike is generated. An event is created. This creates a fundamentally different information pipeline. Conventional transformer. Input. Dense embedding. QKV. Attention. Feed-forward network. Output. Spike-driven transformer. Input. Spike encoding. Sparse spike processing. Spike attention. Output. And hybrid architectures take this idea one step further. Instead of forcing the entire transformer to become spiking, researchers can place SNN layers in front of conventional transformer components. The SNN becomes a biological-inspired filter. Think of it like a massive crowd entering a security checkpoint. The conventional approach allows almost everyone through and asks the transformer to process everything. The hybrid approach performs an initial filtering step. Most insignificant signals are discarded. Only meaningful information reaches the expensive computational core. This is where the math of silence becomes important. Imagine a network containing 1 million possible activations. A conventional dense system may perform computation across essentially the entire representation. But suppose a sparse spiking system activates only 10% of those pathways at a particular moment. Then, roughly 90% of the network is dormant. The dormant neurons aren't a failure. Their silence is the optimization. Instead of compute, we get silence, silence, spike, silence, spike, silence. The amount of actual computation becomes dependent on the information arriving at the system. A conventional neural network largely asks, what is the value of this activation? A spiking system can additionally ask, does this activation deserve to exist at all? That distinction can have enormous consequences for energy efficiency. The SNN doesn't necessarily replace the transformer. It can prepare the information for the transformer. The SNN handles event detection, temporal filtering, noise suppression, and sparse feature extraction, while the transformer handles context, relationships, long-range dependencies, and complex reasoning. So each architecture is used where it is strongest. But there is another piece of the puzzle: hardware. A conventional GPU is extraordinarily good at dense matrix multiplication. That's exactly what modern transformers need. But if your algorithm suddenly says, don't compute anything unless an event occurs, then a conventional GPU isn't necessarily the ideal machine. You want hardware capable of exploiting event-driven computation. Instead of constantly moving enormous matrices between memory and compute units, specialized neuromorphic systems can attempt to process information closer to where it is stored, activate compute only when spikes arrive, and exploit the temporal sparsity of neural signals. This creates a fascinating convergence. The algorithm is becoming sparse. The communication is becoming event-driven. The hardware is becoming specialized for sparse events. The software and hardware are beginning to speak the same language. That is the real promise of SNN transformer fusion. Not simply a faster transformer, not simply a smaller neural network, but a different computational philosophy. Don't spend energy representing everything. Don't communicate everything. Don't compute everything. Compute only when something meaningful happens. And if that principle can be successfully combined with the representational power of transformers, the future of AI hardware may look very different from today's GPU-dominated systems. The ultimate question becomes, can we build AI where silence isn't wasted capacity, but the primary source of efficiency? Let's consider an example to understand this kind of architecture. Imagine a short paragraph from a building monitoring system. A sudden heat spike was detected in the east wing. Sensors reported 42 degrees. Only 2 zones crossed the alert threshold. The cooling system activated automatically. A hybrid model does not treat every word or every sensor reading equally. First, the raw input enters an SNN front end. This layer decides which signals are strong enough to become spikes. Weak or routine information stays silent. Then the transformer receives only the important events and performs the heavy reasoning. In our example, routine background readings produce no spike, but phrases like sudden heat spike and 42 degrees cross the threshold. The SNN turns the paragraph into a small set of events. Most of the input never leaves the front end. Only a few features continue downstream. That is the core efficiency idea. Silence removes noise before the expensive transformer runs. Now the transformer sees a much sparser representation. It connects the events, checks context, and decides what the system should do next. In this case, it can infer that cooling should activate. The final output might be a simple label like thermal alert, or a short action such as activate cooling. The transformer handled meaning. The SNN handled selection. How do you train it? Start with a standard dataset for your task. Train the spike encoder to fire on useful inputs. Train the transformer on the sparse features it receives. Then fine-tune both parts together so spikes and predictions improve at the same time. How do you validate it? Check task accuracy like any model, but also measure spike rate, sparsity, and energy cost. A good hybrid model should stay accurate while activating far fewer pathways. If you want to build one yourself, follow a simple path. Choose your input encoder. Add one or more SNN layers in front. Connect them to a transformer backbone. Track both quality and sparsity during training. Then test on the hardware you actually plan to deploy. The hybrid idea is practical. Filter first with spikes, reason second with a transformer. That is how silence becomes useful engineering, not just theory. Intel's Loihi research chips are one of the best-known examples of this approach. Loihi was designed specifically around spiking neural networks and event-driven computation, rather than simply running conventional neural networks faster. The important thing isn't just the number of processing cores. It's the architecture. A spike can travel through the chip as an event. If there is no spike, there may be no corresponding computation. This makes Loihi-style architectures particularly interesting for robotics, sensors, anomaly detection, pattern recognition, always-on AI, and low-power edge devices. One important correction for a general audience: be careful with the phrase Loihi 3. Loihi 2 is the established Intel Neuromorphic platform. The same broader movement is happening around RISC-V-based research and commercial processors, where programmable architectures are being adapted for sparse and event-driven workloads. The same broader movement is happening around RISC-V-based research and commercial processors, where programmable architectures are being adapted for sparse and event-driven workloads. If there is no spike, the downstream hardware doesn't necessarily need to process a new activation. This creates a powerful combination. SNN, sparse information, neuromorphic hardware, sparse computation. Together, less data movement, fewer active operations, and potentially lower energy. The hardware is finally designed around the algorithm. Thousands of processing elements can stay synchronized to a global clock even when almost nothing important is happening. Why compute when nothing happens? Remember what an SNN does. A conventional neural network might continuously represent 0.21, 0.34, 0.18, 0.42. An SNN can instead communicate silence, spike, silence, spike. If there is no spike, the downstream hardware doesn't necessarily need to process a new activation. This creates a powerful combination. SNN, sparse information, neuromorphic hardware, sparse computation. Together, less data movement, fewer active operations, and potentially lower energy. The hardware is finally designed around the algorithm. But does removing the clock mean zero power? Not exactly. This is an important distinction. Neuromorphic processors don't magically consume zero electricity. Real chips still have leakage power, memory power, communication overhead, background circuits, and control logic. So saying zero power AI is technically misleading. A better description is AI that can become extremely quiet when there is nothing useful to compute. That's the real breakthrough. Instead of energy being roughly tied to how long the machine is switched on, the goal is to make energy consumption much more closely related to how many useful events actually occur. What about the famous 100x efficiency claim? This is where we need to be careful. You may see research papers reporting orders of magnitude improvements in energy or energy delay product for particular SNN workloads. But saying SNN transformers are 100 times more energy efficient than transformers as a universal statement would be misleading. The result depends on the hardware, the model, the dataset, sparsity, precision, latency requirements, baseline transformer, and whether the comparison uses GPU, CPU, or neuromorphic hardware. So the scientifically safer message is, under highly sparse workloads, SNN-based systems can achieve orders of magnitude improvements in energy efficiency compared with dense models. And the potential becomes especially interesting at the edge. Think about devices that must operate continuously but have very limited batteries. Consider security cameras. A conventional camera might continuously send frames to an AI processor. A neuromorphic system can instead focus on changes. Someone enters the scene, spike. Movement detected, spike. Nothing changes, silence. Robots provide another example. A robot doesn't necessarily need to analyze every pixel of every camera frame. It needs to react when something changes. An event-driven vision system can detect movement, edges, collisions, and objects without continuously processing an entire image. Drones are another example. A drone has a limited battery. Every watt matters. Instead of continuously processing enormous streams of sensor data, event-driven AI can focus computation on meaningful changes. Now consider industrial machines. Imagine a factory motor. Most of the time, everything is normal. Why continuously run a huge AI model? A low-power neuromorphic system could monitor vibration or sound continuously and wake up more computation when it detects an unusual pattern. Hearing devices are another natural fit. A hearing device needs to listen continuously, but it also needs to preserve battery life. Event-driven processing can potentially focus computation on meaningful acoustic events. Autonomous vehicles provide another example. Vehicles have enormous amounts of sensor data. Event-driven processing offers an attractive idea. Don't process everything equally. Process the changes and events that matter. Traditional AI. Dense model, continuous values, constant computation, high data movement, high energy. SNN, sparse events, spikes, selective computation. Neuromorphic hardware, event-driven silicon, compute when events arrive. The goal becomes, make the computer work only when it has something meaningful to do. Your brain doesn't stop being intelligent when nothing important is happening. It simply becomes quiet. That may be the future of AI hardware. Always available, highly responsive, mostly silent. We've come a long way. From dense matrix multiplication to sparse computation. From always-on processing to event-driven intelligence. From enormous data centers to AI that can potentially think at the edge with only a fraction of the energy. But this is only the beginning. The most important transformation isn't happening inside a GPU. It's happening in the way we understand computation, intelligence, and technology itself. AI is evolving incredibly fast. The models will change. The hardware will change. The architectures will change. And the skills that matter today may look very different tomorrow. But one thing will remain valuable: your ability to learn, your ability to ask questions, your ability to stay curious. AI will be the only thing in the future. So you need to be on top of it. Keep learning, keep experimenting, keep questioning, and most importantly, keep getting curious. Because the people who understand AI won't simply watch the future happen. They will help build it.